Alright, so for today, our part 2 of lesson 1-2, we're going to talk about some more features of functions. And the first one we're going to talk about is boundedness. Okay? And there's a couple of definitions here, which again are right from your book. You don't need to write these all down right this moment. But ultimately we say a function is bounded below if there is some number b that is less than or equal to every number in the range of f, and any such number is called a lower bound. Okay, same thing with an upper bound. Okay, and then we also say that a function is bounded if it's bounded both above and below. Okay, so let's see some examples of what that might look like. Okay, this idea of boundedness. If we had a function like, say, y equals e to the x, okay, and we looked at the graph of it, okay, it would look like that, an exponential function. Okay. And we would say that this particular graph would be bounded below because there is a minimum value that we get that we actually don't get to in this case. It's an asymptote here. But if we go from 0 to infinity, this would be our range. Okay. Again, the lowest value this gets is it gets infinitely close to 0. Okay. Notice I didn't include 0 because we don't actually get to it. Okay. And if we go up, okay, if we go to the right, it continues to get bigger and bigger. So it's not bounded above. Okay, it just continues to grow without bound, we say. Okay, but on the left-hand side, as we go left, it gets closer and closer to 0. So this particular function would be bounded below. Okay, and if I took, say, y equals negative x squared. Okay, y equals negative x squared looks like that roughly. And so in this particular case, the range is negative infinity to 0, including 0 because we actually do get to 0 for this particular function. Okay. In this particular case, we'd say this is bounded above because it has essentially it has a maximum range value of 0. Okay. It's not bounded below because where do these two branches go? They go down infinitely small, and so therefore it's not bounded below. Okay. Questions so far? If we want to see an example of a bounded function, we can look no further than y equals sine x. Because if we graph the sine function, okay, we know that forever in both directions it just continues to do the same periodic pattern over. Okay, and we know that the high and low for sine are -1 to 1 would be the range here in this case. So this function we'd say is bounded because it's bounded above by 1, okay, that's the highest it gets, and it's bounded below by -1, that's as low as it gets. Okay, so those are some examples of some functions that are bounded below, above, and simply bounded because it's bounded on both sides, up and down. Okay. Okay, questions so far? Yes, because it actually does get to -1 and 1. So those should be brackets. Good. Good. All right. Now, what we're going to look at next then is what we call extrema. Okay, because some functions have extrema, some don't. Okay, and we are going to call these extrema maximums and minimums. Okay, specifically we call them local maximums and local minimums. Okay. And these local maximums and minimums, okay, we call local extremes or local extrema, okay, and we also call them relative extremes or relative extrema. Both of those words are okay. So relative and local are interchangeable here. Okay. Going back to our three functions that I just drew here, okay, this e to the x function, okay, this does not have any extrema because there are no points, okay, that are larger than the others around it or smaller than the others around it, okay, anywhere on this function. This just continues to grow. Okay, this continues to get closer and closer to 0. Okay, it never comes to any minimum value. On the other hand, the parabola that I have here, this one has a local, what would we call that? What do you reckon? That's a local maximum there. So that would be a local maximum. This would not have a local minimum because there is no minimum value in this picture. Okay, if we look at sine up here, there's a local maximum right there, there's also a local minimum right there. Matter of fact, with sine, isn't there essentially an infinite amount of local maximums and local minimums here? Because again, this pattern continues forever in both directions, right? Okay. So this one would have an infinite amount of local maximums and minimums. Okay. All right. Again, if we had a regular parabola, if it was just y equals x squared, of course, at the vertex we would have a minimum point. Okay. Another function to consider, if we had something like this, that was a cubic function, for instance. Okay, that would be another one that has a maximum and a minimum. Now, the reason we call these local, okay, in general, okay, is because of this. If I look at that point right there, and I could find the y-coordinate of it, okay, would this really be the lowest y-coordinate for the entire function? No, because over here it goes way lower than that. In fact, it goes down to negative infinity. So even though in this case the range here would be negative infinity to infinity, okay, is it possible to have local maximums and minimums? Okay, certainly is. Okay. All right, let's take a look at this function. We have a quartic function, fourth degree, and they're going to look at the picture of it. So we have x to the fourth minus 7x squared plus 6x. And if we do zoom 6 here, let's see what we see. Okay, so we can see part of it here. We can't see the bottom of it, so I'm going to change my window a little bit and make it go down lower. So I'm going to change my y-min to negative 20. Still can't see it. It's even down further than that. Okay, so I'm going to change my window again. I'm going to go to negative 30 this time. I'm also going to shorten up my x window just so I can see the points that I'm after better. So I'll go negative 5 to 5. And now I can see all of the points in question, because again, what we're looking for is, do we have any local maximums or minimums? Okay. All right, so let's start with this one. This point right here we can see is a minimum point, and the way we're going to find it is the way we talked about earlier with the minimum command. So I'm going to go ahead and find those. So I use my minimum command under the calc menu. I'm going to arrow over till I get to the left side of that. So now I'm left of it, hit enter. Right of it, hit enter, go back to the middle, hit enter, and I get the point negative 2.057, and the y-coordinate negative 24.057. So this would be a local minimum. Okay. I'm going to go find now that maximum point. We can see that that is a local maximum right there. So I'm going to go maximum command this time, move it up over by the maximum that we can see. Enter left, enter right. Oops, didn't hit enter. Enter right. And the maximum is a 0.456 and then 1.324. Okay. So again, keep in mind that these are not intervals, these are points this time. We're just listing the points that are the local mins and local maxes. And then finally, if we find the other local minimum, enter left, enter right, enter middle, we get 1.601 and negative 1.766, and that would be another local minimum point for this particular graph. Okay. All right. Now, when we answer the question here, what I want to look back at, and we're going to read the question together again and make sure that when we answer it, that we're answering it correctly. Okay? Because this question says, decide whether it has any local maxima or minima. We found that it does. Okay? These are the local maxima and minima. Okay? And it says, if so, find each local maximum value, okay, or minimum value, emphasis on the value. We didn't get that yet. Okay. And the value at which each occurs. Okay, so here's how we want to write this. If they ask us just for the local maxima and minima, okay, so if they ask us for this, okay, they're asking us for points. Okay, so if they had they ended the question at that point, we would have been okay just to say that, there we go, there's our local maxima and minima. Okay, but since they asked the second question, the way we need to present the answer is as follows. Okay. We want to list the local maximum value, so we'll start with the maximum. So we'd say we have a max value of 1.324 at x equals 0.456. Okay, that's how we want to answer this question. Okay, and when we have the same question again, this is what I need to see on your paper. You need to write it just like I showed you here. Okay, so notice that the value that they're asked for here, okay, is actually a y value. Okay, we're after a y value here. Okay, all right, and again, if all they asked you for was the value, then we wouldn't even have this part involved. Okay, we just say there's a maximum value of 1.324. Okay, but they ask us where it occurs also, so we'll put it in the same sentence and we'll write it just like that. Okay, we would say a min value of negative 24.057 at x equals negative 2.057, and another min value of negative 1.766 at x equals 1.601. Okay, so this would be the official answer for this particular question. Okay. Questions so far before I make another comment about what I wrote? Okay. Now, every one of these here that we can see in the picture are considered local maximums or minimums. Okay, but this one is actually more special. Okay, it's not only a local minimum. Okay, but isn't this the lowest that this function goes? Okay, out of any points. Okay, in fact, wouldn't this the value in that bottom value be the left-hand side of our range if we wrote it? Okay, because this is as low as it goes. So not only is this one a local minimum, okay, but it's also an absolute minimum. So this is a local and absolute minimum. All right, whereas these are just locals. Okay, but that one that goes down to negative 24, which is the lowest that this function gets, that we call an absolute minimum. Now, does that make it not local? No, it's still local, okay, but it's also absolute. Fair enough. So why isn't this the absolute max then? If there's only one max on either side of that, where do these other branches go? They go way higher than 1.324, don't they? Okay. In fact, they go up to infinity. So therefore, that would still just be considered a local maximum. So in this case, would there be an absolute maximum? No. Okay. Questions so far? Okay. All right. What we're going to do